machine and the flow? No. Hello and welcome back to Calculus 3. Today on the menu, conservative vector fields. So we start with the definition of the conservative vector field. So a vector field F, get glasses, is said to be conservative on the region in 2D or 3D if there exists a scalar function phi such that the vector field is the del phi on that region. So this is the definition, but you have seen this before. You know that del is the gradient is going to give you the vector of partial derivatives, right? You know that, hopefully. So if you have f of, let's say, xy to be 2xy squared minus cosine y, you can find the del f, which is the partial derivative in respect to x, which is just 2y squared, and then partial derivative in respect to y, which is 4xy plus sine y. And look what you got. You got the vector. Well, this is a vector field, which makes this f, which makes f equal to phi, and phi is called the potential function. So I'm going to use, so this phi is called potential function. What is a potential function? Potential function is a scalar function which generates field, right? Vector field. Now, we are going to, definition says that the conservative vector field is the one that has a function which generates it. You know that you can't integrate everything, right? You can differentiate everything, but you can't integrate everything. So you are not guaranteed, if you have a field, you are not guaranteed that you will have a function that generates that field, a scalar function that generates that field. When it happens, the field is labeled as conservative because such a function which generates it exists. And we are learning today the procedure of how to obtain that potential function if the field is given. But you don't want to go and waste your time looking for something that might not exist. So we better have a test to check if the field is conservative. So step number one, check if the field is conservative, because if it is, you are guaranteed to have the function. Go ahead, spend hours, find it, right? If you don't get a conservative field, sorry, don't waste time. So test for conservative vector fields. This is what you are also memorizing. So test for conservative vector field says partial derivatives, these following partial derivatives have to be, so all of the following equations must hold. So for R2, there is only one. Partial f divided by y, partial f partial y is partial g partial x. So that's the only one because you're in 2D, right? But for 3D, you have three combinations. Partial f, partial y, and they all have to hold. Partial g, partial x, this is the same one as above. And then partial f, partial z is partial h, partial x, right? You see that they're mixed. And then partial g, partial z is partial h, partial y. So you see how you have all combination. You have x with y, x with z, y with z. Right? X and y, x and z, y and z. You have functions f, g, and h. Just mix them up. It's not that difficult to memorize this. So when you have a field given, what you have in front of you are f and g, or f, g, and h. And then you just run these partial derivatives to make sure that the field is conservative. So let's check if e to the x cosine x, comma negative e to the x sine x is a conservative vector field. Is this conservative? Well, here is your f, here is your g. Just do it. What's partial f, partial y? Oh, wait, hold on. These are... Holy nightmare. I really messed this up. Much better. So e to the x cosine y and negative e to the x sine y. So what's partial f, partial y? Partial f, partial y is? Yes? And what's partial g, partial x? Uh-huh. You know what the easy analogy for this is? You're checking for even and odd functions, okay, in pre-calc 1. So it's just a little bit more involved, but technically, if you know the formula, you should be able to compute this. Just be careful. This stuff is extremely easy and extremely tedious at the same time. This is the definition of annoyance, not definition of something being hard. So collect your thoughts and grind through it. Cool. I just proved that this is conservative.
I thought you said all of them have to hold.
There's only one, it's 2D. Right? If you look at the purple one, the 2D case only has one formula to worry about. So the $1 million question is now, and the most important part of everything, what is that ghost function, the potential function which generates this field? So my question is, what is phi? Because now I know it's conservative. Which phi will generate this? All right, let's unleash the procedure. What? So now, I know that this is partial derivative, right, of phi, and I know that this is partial derivative of phi in respect to y. So I'm going to start this by integrating e to the x cosine y in respect to x to build it up. So if I integrate this in respect to x, I get e to the x cosine y plus constant in terms of y. Now, this is new in your life now. So far, when you integrated, you always put plus c because that was supposed to be some kind of number. Now, it's plus c as a function of y because if I am to differentiate this using partial derivative, this is going to die. So if this is maybe y squared, it's going to be 0. If it's 3, it's going to be 0. So I have to leave that as a possibility to be a function in terms of y. Do we all see that? Cool. Now, this is already stage 1 answer. This is already phi, because I took the partial derivative and integrated it. So this is already phi. But I have that cy there. So I can do better, right? So what I'm going to do now, and I'm going to actually put this over here. This is already partial answer or solution, okay? So now what I have that phi of xy is equal to e to the x cosine y plus c of y. So this is what I have so far. And now here's the genius step. Differentiate this partial answer in respect to y to get phi y and equal it to this to figure out what's missing. And I don't want to break it. It's so awesome.
I'm like, oh God.
So now, phi y, differentiating this in respect to y, is going to be negative e to the x sine y plus c prime of y. Because when you are differentiating function in respect to...
Wouldn't it be positive e?
What? No.
Cosine goes to negative.
You are
I thought
differentiating...
you were integrating it though.
No, I said differentiate. You have the notation in front. Right? And now, here, in blood, equal to negative e to the x sine y, which is this puppy. Set them equal. From here, you get that c prime of y is equal to 0. Well, this is your function c dy equal to 0. Right? So, you integrate, right, separation of variables, integrate both sides, and you get c is equal to 0. Well, this one was easy. So now you go back to your partial answer, plug that 0 there, and you get that phi of xy is just e to the x cosine y. You know what? Check it. Do the del phi. Compute del phi. What do you get? When you differentiate in respect to x, you get e to the x cosine y. When you differentiate in respect to y, you get minus e to the x sine y, which is exactly what your vector field was. So you know that this is the answer. You found a scalar function which, through del, creates the vector field.
So don't all although all functions get a vector field because it's continuous, they all have a gradient if they have.
Very good. You understand that way. But the other way is the problem. Every function that I can think of, you give me anything, I will be able to generate fields from the function.
Yeah.
My question is, and this is where science lives, when I give you the field, can you give me the function? And that can't be done all the time. You cannot go and observe tornado and have equation for it. You go to tornado, you toss a whole bunch of junk in it, and you collect data points, and those data points are data points for the vector field. Then you extrapolate stuff, you figure out what the vector field is for the tornado, then you check if that is conservative, and then you try to find this. And then it plots the course. You see that? All right? So, in
Like what they always say in
sciences,
science,
what you
can't
can
observe something, observe what it affects.
yeah, but see that's the trick. So you can measure electric field, you can measure magnetic field, you can measure gravitational field, right? And once you have the field, do the conservative thing and hope to be able to put into this. This is what your work is up, and why you have to know these things. So it's not just, compute this little blah blah and be done. We have to do a 3D example because it's much worse than this one. Yes?
Real quick. Like, because in DPQ you can multiply by mu, that's not exact,
That's to solve differential equations. Yeah. That's
That's
So what kind of question of this is going to be on the final, 2D or 3D?
probably 2 because you don't have time for. You'll see now the 3D. It should take us the entire 15 minutes and then we'll be done.
You're going to teach in DPQ as well.
Do what?
Is the next part you're reviewing in DPQ as well.
No.
I don't know. I'm trying to compete and I'm trying to decide if I read or not.
Oh, definitely not. It's all stream. Okay, so let's take a look at so vector field is given as, I just don't want anything diabolical, so I stay here forever calculating things. Here, x cubed, it's probably gonna be disastrous, but 2y negative z cubed. So this is the vector field. Someone says find the potential function, and you say, hold on, comrade, the first thing I have to do is to make sure that this is conservative, because if it's not conservative, you don't want to waste your time, right? So conditions to check if it's conservative. Conservative, there we go, question mark. All right, we have partial f partial y equals to partial g partial x. Let's see. Partial f in respect to y is 0. Partial g in respect to x is 0. 0 equals 0. Okay. Partial f partial z partial h partial x. You're just mixing x and z. 0 0 again. Thank you. Partial g partial z partial h partial y. Beautiful. All three conditions hold, therefore this is conservative field, therefore potential function exists. Let's go have fun. Phi x, phi y, phi z. We start by integrating phi x. I integrate phi x.
I'm sorry, in DPQ what one or the other?
You can always, yes.
So why don't you start with the 5y, because you just go to y squared when you integrate it. It'll be a lot easier.
It doesn't matter.
Oh.
So I'm integrating x cubed dx, and that is going to give me x to the 4th over 4 plus a constant function in respect to y and z.
That's always in respect to the other two variables.
Yes, because if you are to take the derivative, right? So now this is already the partial answer. Maybe I should, I'm going to box it in purple. It's a partial answer. So this is already your phi x, y, z. Now I'm going to differentiate that one in respect to, let's say, y. And if I differentiate that in respect to y, I'm going to get partial c, partial y, right? That's all I'm getting. Partial c, partial y when I differentiate. The derivative of x to the 4 over 4 is 0 because I'm differentiating in respect to this. And I am setting this to 2y, which is the next one. Now look what you're doing. You have a differential equation here. You have that your partial c, well, you can call it now dc, is equal to 2y dy. Integrate both of those, and you get that your c is going to be y squared over 2, and 2 cancels, plus I'll put some constant k, which is in respect to z now.
And then you use that to substitute with
Yeah. So now, as you can see, I have better answer for phi. Was another step. So I have x to the 4 over 4. I am adding y squared to the mix, and I still have this k of z to deal with. So now this is, again, a partial answer here. Partial answer, level 2. All right, that was a level 1 up there. So I'm going to differentiate this in respect to z. I get 0 plus k prime of z. And I'm setting that equal to phi of z up there is negative z cubed. Integral of k dz is equal to negative z cubed dz. So I am getting that k is equal to negative z to the 4 over 4.
Excuse me? So like the negative z3 was already in the vector field, right?
Yeah.
That's what we started with? Okay.
Mm-hmm. Right here.
No, I just forgot. Okay. I thought that was a 2.
It's, well, I crossed my z's for that reason.
No, I mean a square instead of a cube square.
So z cubed over 10 is over plus 4 plus some number blah. There we go. And finally, I have my potential function phi, which is x to the 4 over 4 plus y squared minus z4 over 4 plus whatever blah is there. And that is the final answer. It's a scalar function. Now, if you have a point, you can figure out what blah is. No, right now, right? Those are initial conditions and things. But this is how you find potential function. Now, you will see this in differential equations. Those of you who are going, right? You can just say to everyone, he's not joking. To solve exact equations. Okay, to solve exact equations, and each one of these was the differential equation which we dealt with separation of variables and so on. Once you take differential equations class, you will enjoy that there.
No, you won't. You won't enjoy it.
Everyone is different, like snowflakes, okay? And bunch of snowflakes do enjoy differential equations. And some just melt and
I'm one of those.
cool. Well, that's a record time for me. We have time for one more, I guess. I don't know.
Yeah, sure. Make this actually complicated. You know what? This was actually pretty simple when there's no e's.
Could we do this in 4D?
I was about to say, let's pick a one with E. No, I don't know what they have. Let me see what they have.
Is it possible to do this in 4D?
Yes, because it's just gonna be another one, and you just do the procedure one more time. I hope you guys saw that I did the 2D procedure twice now. It's the same procedure going. Oh, actually, sorry, I can't. I can't. We have a fundamental theorem for line integrals.
Yay.
You remember the fundamental theorem used to be the f of b minus f of a, right? The definite integral. Well, this is it just for line integrals. So when you have the line integral, you can compute it like this. Where f is del phi, conservative obviously, for all points A and B in R, which is in R2 or R3. So fundamental theorem of line integrals. Now there's a cute proof there that shows this. What are the A and B? A and B are the endpoints of your smooth curve. So if you parametricize something over the unit circle, it's from 0 to 2 pi. If you have a line segment that goes from 0, 0 to 1, 1, or a line segment that goes from 1, 1, 1 through 5, 5, 5. So those are your A and B, and you compute your, you have to understand that your function phi is going to have the same amount of dimensions and variables as your point has. So capital A could be a 2D point or could be a 3D point, depending on if function phi is a 2D or a 3D. So this is essentially the same as your good old Calc 1, f of b minus f of a, because your integral was from 0 to 2, right? So a was 0 and b was 2. Now your a and b are capital letters because they take on 2 or 3 coordinates to compute. It helps with computing the line integrals. And I think there is one more. Yes, there is one more thing, that the integrals on closed, this is a really lifesaver for later on in mathematics, to realize that the line integrals along closed contours, closed curves, is 0. Because you go and you come back to the same point. So phi of b minus phi of a, same, you're subtracting the same number. So remember the difference in physics between distance and displacement?
Yeah.
That's this. So if you go from, let's say, you go from 1, 1 to 5, 5, there is the distance and displacement you're covering there. But if you go from 1, 1 to 5, 5, and then you take a semicircle back, your starting point and your end point are both at 1, 1. When you subtract them through this, you get 0. So I'm going to actually write that theorem down, and this is where you have those cool looking integrals. So line integrals on a closed curve. Not that you guys did class prep, so.
Oh, yeah, we talked about that.
We've talked about that.
Yeah, here's my question.
Absolutely no need. So on the conservative vector field,
What percent of our grade was
5.
5%. That's 5% that I use.
Yeah.
Everyone can, even me.
No, so seriously, it takes how long to do it per thing times how many lessons again?
Actually, like 0 to
Can
if
we
you do
make
it during
them
class
up?
and just hand it at the end of class.
Can I make up set?
Yes.
Oh. Ooh.
In a conservative vector field, look at this. Integral on the closed curve C, f dr, or you can put any other form, is 0. Nice.
What's that different integral sign mean? It means a closed loop?
Yeah, that the C is a closed, so unit circle, or you integrate around the square, ellipse. Yeah, I don't know elliptical integrals.
And that means the rotation thing. That's what you So,
Ta-da! All right. Good. So that's it for the lecture, guys. I will see you all on by stream.